All right. We have a plate. It's sitting on, well, it has two react supports at point B and at point A. Not very clean, but both of them are actually on horizontal surfaces, something like this. One side, the other corner at point C, is held by a cable. And we have a 300 Newton force applied to this point. And some random moment or moment of a couple, or we can just think about it as just a moment, 200 Newton meter in this direction. So this is the situation of this plate, I would say. Let's see what the problem statement says. It says the homogeneous plate, I would say, let me see what it says, plate, let's say has a mass of 100 kilograms. So in this case, we are given the mass directly, meaning that we can neglect it, and is subjected to a force and couple moment, well, it's just a moment, you can see, along its edges. Now, if the plate is supported in the horizontal plane by a roller at A, a ball and socket joint at B, and I guess you could call it as a cord, as a rope, and a cord at C. If that is the situation it is in, and it's in a static equilibrium, determine the components of reactions, I would say, at these supports. Let me clean this up. All right. So we have a plate, it's in a static equilibrium. This is the situation. It is held by two supports in A and B. B is a ball and socket joint. A is just a roller, and it's also held on the other side by a rope or cord. We also know 300 Newton force is applied on that edge, and a moment 200 Newton meter is applied in the other edge, and we also know the mass. And it says homogeneous. The reason you see the word homogeneous, it means when we have an homogeneous plate, so the point that the mass or the weight, we said, well, one of the forces we have to take into account, weight has to be applied is exactly in the center, right? Because it's symmetric. So basically the force has to be applied for at least the mass or the load, the weight, well, we're using force. The load for the weight should be applied exactly in the center. We'll see later on during this course, a couple of weeks from now, maybe more, how can we actually calculate the center of gravity or center of mass for a structure. But for now, it's a homogeneous plate, so it's exactly in the center. All right, so start with free body diagram. That's where we start. Let me, the same thing as uniform. Exactly, it's the same thing as uniform. Uniform is usually used for a bar. When we have a bar, we say uniform bar. Homogeneous plate, homogeneous, I guess, is more used for higher dimensions like plates or 3D objects, because we say, well, the mass is not homogeneous. If it's not homogeneous, it means that one side, let's say, maybe it has some deficiency in this part and it has more mass on this part, so the center of mass is going to be moved. It's not going to be in the center of the plate. But yes, it's the same thing. All right. So let's draw the free body diagram. I'm going to draw the plate here. I'll just do my best to draw it. There we go. Could be even better if I move this and then move that. There you go. All right. Forces. Start putting forces on this. Now we have 300 newtons there, so I'm just going to leave it here. We have the moment. We're putting all the forces and moments. We're drawing free body diagram moment here. Let me show the moment. I'll use the names for these. Let's call this F1, 300 newtons. And call this, I'm going to call this M prime, so we can use M later on if we need the letter, 200 Newton meters. All right, so what else? These two are the obvious ones. I'm isolating the plate, right? So the whole thing is coming up. One force of the roller, exactly. So roller, I'm glad you remembered, but roller, if you remember, it was just pretty much just one force, right? Just one force. Is very similar to smooth contact. Since we have a roller at point A and we are taking that out, we have to compensate for it by just one force, horizontal force. We don't know that, so we'll just call that, let's call this A, point A, and it's in Z direction. We'll call this AZ. I should always start with defining my coordinate system. It's a better practice. So I'm going to define my coordinate system in this, well, you know what, not there. Actually, you guys tell me what is the best point to define the coordinate system and put the coordinate system there. Do you have any guess? B, right? Yeah, thank you, Richard. Make B your origin. Exactly. This is the best option because point B is going to have most number of unknowns. B is a ball and socket joint and is going to introduce 3 unknowns to my system. So let's just use that. Following the advice I gave, I have to follow my own advice, right? So let's just put X, Y, and Z here. This would be X. This would be Y, and this would be Z. I'll put my origin there. All right. So a roller on a rough surface would have been a little more challenging. You would need more than one because I don't even not sure if we talked about this, but we need more than one. I also have to take a look at that table, right? I can take a look at the table and I can tell you. But yes, generally speaking, as far as I also remember, we had just one, because the force. Let me think about it. Let me see if I can phrase it better. The force is one force still, right, in space, but now we don't know its direction. But since it's a roller, it just goes in one direction. Now, actually, I have a roller still here from the last time. So if it's a roller, it can go in this direction, and the contact point with the surface would be horizontal, in Z direction in this case, like upward, perpendicular to surface. But let me show it this way. But if there is a friction, then the friction is also preventing it from moving in the other direction, this direction. So we had to put another component. Yeah, I spent 2 minutes explaining just what you said, Richard. I could just say yes, would have been understood. Yes, just I mean we would have needed an extra component there. All right. So looking at B is a ball and socket joint. We're gonna put 3 components there. Let me see, how should I put this? Well, obviously I'm just gonna go with some default direction. So let's just go with this upward, this one in this direction, and this one in this direction. So they're all positive. I'll call this with point B. So let's call this BX. Let's call this one BY and this one BZ. This being point B. What else? Anything else that I'm missing? Or we're good? Cable at C, exactly. So we have to take into account that one as well. This is going to be, let's call this TC. So follow the namings. We usually use T, so it's the tension. Are we good? The weight, exactly. Thank you, Colin. We have to also take into account the weight because we are told that it's 100 kilograms. And as I said, since it's homogeneous, it goes directly in the center. And let's call this, I guess, W, which we can actually find. I don't want to make it crowded there, but it's 100 times 9.81. All right, I think we're finally done with the free body diagram. So this is our free body diagram. All right, so let's start with the easy part. Represent the forces. Well, actually, I can just go directly and hopefully you follow. Let's see. Summation of forces should be 0. What does that mean? It means summation of forces in X should be 0. Vector sum of forces in Y should be 0. And summation of forces, components of forces in Z should be 0. So what do we have in X direction? The weight of the plate. Oh, that's from before. What do we have in X direction? As crowded as this is, I have to make it a little better. Right? This does not belong. This belongs to this one. So don't get lost there. We have BX. Anything else in X direction? Not really. Yeah, just BX. So BX is equal to 0. Meaning that that ball and socket joint is not handling or tolerating any force applied to it in X direction. Good for us. How about Y direction? We have BY. What else? Keep in mind, we're looking at forces. Nothing in Y direction, just BY. So that's also 0. It's telling us that ball and socket joint is not tolerating or handling any force even in Y direction, given X, Y, Z, the coordinates that we gave. All right, so far so good. We got rid of 2 forces, BX and BY already. How about in Z direction? What do we have in Z direction? What are the forces in Z direction? AZ plus BZ plus TC. Yeah. So AZ plus BZ plus TC minus, exactly. Thank you guys. Sam and Connor, both are. Oh, Elizabeth. We'll figure that out. I'm happy to see that. Minus 300 downward. And minus, let's do the math for W. W would be, I can just put it here, don't get mad at me to make it crowded. 9.81 times 100, which makes it 981 is equal to 0. All right. Good and bad. We got rid of 2 forces here. Kinda, or we found them. There's 0. 2 components. Now we have one equation there, and we have 3 unknowns, right? We have AZ BZ and TC, which we don't know what they are. So one equation, three unknowns. It's not going to work definitely. We need more equations. How do we do more equations? We look at the moment equation. Summation of all the moments should be 0. Now, before I do that, let's just do it this way this time. Well, obviously, if we need to find moments, we have to find the moments of all the forces about point. I'll call this. Let me go with the same color. Point B. Right. That's why we put the origin there. We said let's put the origin somewhere. We have most the number of unknowns. So we know that later on we're also going to take the moment about that point with most number of unknowns. So let's just make our life easier. So this is point B. So in order to find the moments, I have to find how far each force is, or the line of action of each force is from point B. Right? That I'm going to find the moment about. So let's go about it this way. Let's call this, I guess, R1. I can do a good job there. So the problem with three-dimensional problems is things get a little crowded. I try to use colors so hopefully you can follow. I call this R1. Call this one, if it works, there you go. Call this one R2. Let's call this RC. Well, it's from point B to that force. And how about calling this just RA also? This is also RA. A lot going on in that figure. RA. All right. So to find these, I have to find the coordinates of B, C, and A, and probably have to find the coordinates of that point, the center, whatever that is. We have to call it something. What should I call it? It makes sense. I can call it just point. We have point B. Let's just go ahead and just find if I'm running out of name. Let's just find them points one by one. Point B is 0, 0, 0. It's the origin. That's easy to do. What is point A? Can someone tell me what is the coordinate of point A given the coordinate system we have? Zero minus 2, 0, exactly. That's actually correct. 0 minus 2, 0. Coordinate of point B. Oh, sorry, we did B. Coordinate of point C. Coordinate of point C would be, well, this is point C. That's where this is minus 3. Exactly. Thank you. Minus 3, 0, 0. Let's keep it that way. Maybe I should, yeah, call this point D. We don't have point D, so let's call this point D. What is the coordinate of point D? Pretty bad naming of it there. We just call that RD, then it would have been easier. What is the coordinate of point D? It's exactly the center of the plate. So what do you get? Minus 1.5 in X direction, right? That is correct. Minus 1 in Y direction is also correct. And 0. Great, thank you. So now we have the points. Let's form the vectors. Right? Some of them are pretty easy. RA, well, it's along y-axis in negative direction, so it's just minus 2j. Exactly as the point A. Guys, stop me when you, if you cannot follow any of these steps, right? I'm just going as assuming that, things make sense. RC, let's do RC, would be missing a point at F1. That is true. Yeah, pretty bad naming. You're gonna have to put a name there too. Let's, okay, for the sake of argument, let's put it E. I'm sorry for bad. You don't do that. Let me just put it here. So, what is the coordinate of point E? Let's just put it so we have it. What is the x, y, z for point E? That's where point force F is applied, or F1 is applied. Minus 1.5. Right, that's the, well, I don't know how did you get minus 1.5. Let's double check. Actually, it's correct. No, why do I doubt you? I always should trust you guys. Minus 1.5. Y is minus 2 and 0. Exactly. Thank you. So, again, let me make this overcrowded. So let's just form the vectors right here when we have where we have the points. So we have RA, let me do it again, is going to be minus 2j. We have RC, these are the easy ones, so I'll put there, is minus 3i. Now let's do R1 and R2. So what is R1? R1 is where point E is, right? So it would be minus 1.5i minus j, if I'm not, no, minus 2j. Why am I doing this? Minus 2j, again 0. Also, I just don't put that there. Yeah, this bad name is even throwing me off. So R2 is where point D is, right? From point B origin to where point D is. What is R2? I'm just gonna wait a little bit so everyone can actually digest what we're doing. Yes, thank you, Richard and Vosha. It would be minus 1.5i minus j, exactly. So I believe I have everything I need. I have, well, I didn't write F1, F2, and F1, W, A, but you can see the directions there. So technically we have them represented in, I'm not going to write them down so things don't get even more messy. But we have position vectors and we have the forces, and we can, position vectors are represented in Cartesian coordinate, and we can also write these vectors, force vectors in Cartesian coordinates. I'll just find the moment about point B. That's what we were trying to do from the beginning before this whole mess. So we have RA cross FA, right? If I call it FA, you know what? Don't kill me, but I'm just going to write them separately. So later on, when you're just following this example, things are less messy. So let's call FB. Would be BXI plus BYJ plus BZK. Some components that we don't have. All right, FA as AZK. So we just follow the, it was in A direction, right? Minus AZK, but just take it AZK. I think it's going to end up being AZK anyway. And FC, which we call it TC, TCK. I just represented these at least. What else? We had F1 and F2, right? We had F1, 300. So I'm just going to represent that as F1 was minus 300, was downward, if I remember correctly. And for the sake of arguments, since I define this R2, I'll define W as F2. Again, could that be much less messy? But since I defined that R2, I'll call this F2 as W. And I'll say F2. No, it's W downward. It was 900, and so it's going to be minus 981. Okay. All right. At least now we have everything there. So now let's do this. Is equal to 0. Right? It's going to be RA cross FA plus RC cross FC. We know FB is not needed. Plus R1 cross F1 plus R2 cross F2. Plus, keep in mind, we had all these forces creating moments, and we have M prime there. M prime is the moment that is already there, couple moment, and it's in Y direction, so minus whatever value we get there. I'll just write it here as a vector for now. M prime as a vector. All right, same story. I'll try to make it a little shorter. Right? Actually, the first one is easy to do. So let's just these two. This one and this one. The first one will give you R1 cross F1, right? I, J, and K. R1 was going back minus 1.5 minus 2. So minus 1.5, pretty ugly one. Minus 1.5 minus 2, 0. F1, I represented that here, is 0, 0, minus 300. 2 is R2 cross F2. I, J, and K. F2, well, that's my R2. R2 is minus 1.5 and minus 1. Right? So minus 1.5, minus 1, and 0. And F2, I have it there, is 0, 0, minus 981. If you do these two, let me give you the numbers. From the first one, you get 600 I minus 450 J. From the second one, you get 981 I minus 1471.5 J. RAFA and RCFC, the reason I didn't write it there because I'm hoping that you remember that whole IJK. It's going to save some time. Since RA is minus 2J and FA is AZK, right? J times K pretty much gives you minus 2I. So this becomes, I'm just going to write it here. That's why I didn't write it that way. You can always feel free to write the whole expanded version of minus 2I. Well, actually, it has AZ as component, so it becomes minus 2AZI. And RCFC, well, FC only has components in one direction, is TC in K direction, and RC is minus 3, so 3I times K, I times K would be minus J. The negative there, this becomes 3TCJ. So putting everything together, I'll write it here, try to write it here. Summation of the moment about point B should be 0. From there, this one is minus 2AZI plus 3TCJ. From the first one, I got plus 600I minus 450J. And from the second one, I got, if I didn't make any mistake, 981I and minus 1471.5J. And then we have M prime. What is M prime? Can someone tell me what is M prime? Looking at free body diagram. 200. Well, it is 200, but minus 200, right? Because it's the direction of it. It's, if you look at y-axis, it's in the opposite direction, M prime. So that becomes minus 200. exactly, minus 200j. Thank you, guys. Minus 200j. This should be equal to 0. Now, since it's equal to 0, you know, x components, y components, and z components should be equal to 0. I can just separately write them here. So, I components, which is basically what we are trying to say is summation of moments in x direction is equal to 0. What does that give us? Go back and pick the I components. Minus 2az and 600 and 981, and these are the I components. So I can just write it directly here. Az becomes equal to, if those two go to the other side, it was 981 plus 600 divided by 2. That'll give you 790.5 newtons. This is Az. J components, summation of forces in y, moments in y direction is equal to 0, pretty much. That's what we're trying to say. We have 3Tc, minus 450 can go to the other side, 1451.5 and 200. They all go to the other side and we can sum them up. 450, this one and this one. All right. So Tc becomes 450 plus 981. No, sorry. Am I right? Let me double check. 450, 1471 and 200. All right, now it's correct. 450, 1471.5 plus 200. All the components, right? And the coefficient for Tc was 3, so we can divide it by 3. From there, you will get 707.17 Newton. And this is Tc. All right, almost there. So we found all the way back. We found Bx, By. We found the relationship between this one, the relationship between Az, Bz, and Tc. I'll keep that here. Now, from the moment equation, we found Tc and Az. So since we have the relationship between Az, Tc, and Bz, we can actually find Bz from there. So from star, we can find Bz, which would be, things go to the other side. I think the value where there was 300 plus 981, and then minus Az minus Tc. If you do this math, you will get minus 216.67 Newton. Now the direction is, let me put it again here, this is Bz. Now the direction is not correct. Right? So what this tells us is that, well, Bz is, the magnitude is correct, but since you took Bz up, oh yeah, it seems like it. Seems like Tc is, or Az is too much. So the direction should be flipped. Right? The opposite of what we assumed. Right? That's interesting.